Hello everybody. I hope we're doing well. Okay, so what I'm going to do today is I'm going to talk about electricity and static charge. Today's lecture is on static charge. The next one I give will be after doing some practice with static charge, and that's going to be on current, and that's going to be a lot more work and a lot more practice to it. This one is going to be, we have a worksheet with static charge. You're going to practice that a little bit. But it's going to be a shorter lecture. When you look on PowerPoint, my PowerPoint slides are all together as one whole lecture, but I'm splitting them off, okay? So you'll go up until you see current if you want to look at my PowerPoint lecture. Okay, but here we go. So let's talk first about static charge. This is something you probably already knew about. If you knew anything, if you've ever learned anything about electricity, you knew about static charges, okay? One thing first to know is that if you have, or the way an object has charges, if there's too many electrons, it would be a negative charge. If there are too few electrons, that would be a positive charge, okay? Now, when you probably heard a long time ago that if an object has, or if two objects have a positive charge, then they're going to repel. Okay, if two objects have both have a negative charge, they're going to repel. So you've already probably heard opposites attract, right? And maybe you can look it up if you don't know it, but Paul Abdul back in the day had an awesome song called Opposites Attract with DJ Scat Cat. So you could watch this video on YouTube. I'm sure you'll find it somewhere with her dancing with a cartoon cat, and it might be inspiring, and no, it won't be. But anyways, there's a video on that, which has nothing to do with physics, but it is about opposites attract. All right, so you should know that already. If you have two charges that are the same, they're going to repel, positive, positive. Or if you have two charges that are negative, negative, they're going to repel, that's fine. If you have a positive and a negative, they're going to attract. Okay? All right. Now, understand that charges will not be created or destroyed. It's just that charges pass. So electrons are being passed from one object to the next. If you rub one object against another object, one might become positive, one might become negative. All right? But the number of electrons in the universe are basically going to be the same no matter what. Okay. Now, quick little side note. The word electricity actually comes from the Greek word for amber, because electricity, or amber, what they found out was that when you rub amber, you get a charge to it. So when you rubbed amber against your clothing, it would get a charge, and they started to notice static charge. So apparently amber is more than just valuable for aesthetics, but they could use it for electricity. All right? Now, here's a formula, and this is the big formula that you need to know, and this is called Coulombs Law. And it's talking about the force of attraction between two objects. Okay, let's say we have two charges. All right, it doesn't really matter if it's positive or negative, or if they're both the same, if they're going to repel or they're going to attract. Let's say both of these are charges. And let's say, and the way we measure charge is in coulombs. Okay, they'll do a capital C or C-O-U-L, but coulombs are going to be the units for measurement for a charge. Now, the strength of the force is going to depend on a couple things. One, it's going to depend on how much charge each one has. Okay? Also, it depends on how close or how far apart they are. So, if I have two objects that are positively charged, they're going to be pushing away from each other. I'd be multiplying two positive numbers. If I have one that's positive, one that's negative, that's going to be attracting, then I'd put a positive number here, a negative number there. All right, so what we're going to do is we're going to just plug it in. To get the force, we're going to first take the number, which is going to be a constant, which is the letter K. So lowercase k is just a number, 9 times 10 to the 9th. Okay, then I'd multiply the amount of charge I have here and multiply the amount of charge I have here. And if this is positive, if I say it's a positive charge, make it a positive number. If this is a negative charge, make it a negative number. Okay, so you multiply these two numbers that you were given in coulombs. And then you're going to divide by the distance apart squared. Okay, think about it. If these two objects are closer together, they're going to have a stronger force of attraction or repulsion. okay, depending on positive or negative. If they're further apart, they're not as strong of a force. Okay, so it's the distance apart. We use the letter R for radius, but it just still means distance. Okay, and we're going to square that number. So it's really, really important, the distance apart. Okay, the closer together, the stronger the force. The further apart, the weaker the force. Okay, so you're going to plug and chug those numbers in, and you're going to get the force. Now, what do you think the units are going to be for force? Yes, that's right. Very good over there. All right, it's going to be newtons. So you're going to measure the force in newtons as always. Okay, now I say, does this formula look familiar? And it really shouldn't yet, because I haven't talked about universal gravitation. But if I talked about Isaac Newton's universal gravitation, you would see that, yes, that looks a lot like the force of gravitation formula. But don't worry about that because you haven't seen it. There you go. All right, now when we talk about let's say I don't want to worry about the force, but I just want to know about how much electric field this has. Okay, so electric field is a lot like the acceleration of gravity. Okay, if we talked about me and the force of gravity that the earth pulls me onto, right? I do my mass times the acceleration of gravity. Well, the same thing with electric field. Electric field is like the acceleration due to static charge. We call it electric field, and it's just saying how intense of an electric field does this have. And it's just going to be equal to, again, that same constant K, which is 9 times 10 to the 9th, okay? So it's going to be the constant K times how much charge I have. If it has a really strong charge, then it would have a stronger field. If it has a weaker charge, it's going to have a weaker field. So I'm just doing K times 1Q, okay? And then divided by the radius, because if I want to measure how much static or how strong the intensity of the static field is, if I'm closer to it, I'm going to get more intense. If I'm further away, I'm going to get less intense. Okay? So it's just going to be how far away you are from where you're measuring it. Okay? So if you look at it, it's the same exact equation I just showed you, but without the second charge. If I have 2 charges, that means force. If I have only 1 charge, it means the field this is giving off. Okay? Now, quick little side note, you could also just take that field, multiply it by the second charge, and get force again. Okay? All right. You can watch a video on Van de Graaff generators. It's connected in my notes to Steve Spangler. All right, so I'm just stealing it off of his YouTube page. There's another one on a Wimshurst generator. It's got some funky German music to it, but those Wimshurst generators were actually used to spin, and back in the day it was kind of like a party favor to have these two plates basically spin and get a charge and show off the sparks. Okay, the last thing I'm going to say, so we have electrostatic induction. Actually, so I have 2 more slides. Electrostatic induction, this means this. Let's say I have 2 objects that are not touching each other. You can actually get an object to charge another object by bringing something close to it. Because what's going to happen is, let's say I have this is charged, okay? Let's say this is charged and this is not charged. I'm going to hold it like this. Let's say, but I have electrons and protons. I have electrons on here. Well, if I bring this, and let's say this is negatively charged right now. So let's say the eraser is really negatively charged. Well, all the electrons from here are going to push away the electrons over here. And what you're going to notice is the electrons on this pencil will try to push further away because they're repelling and be closer to this eraser side. Okay? So what you'd have now is this side is going to be what? Positively charged. This side, because it has more electrons, will be negatively charged. And all of a sudden, even though this is still not charged, the electrons have started moving around, okay, to be not touch it, or to kind of be rearranged. All right. Now, let's say right away I snap this pencil in half. All right, cut it in half. Well, then what would happen is this side would be positively charged, and this side would now be negatively charged. And we call that electrostatic induction. I'm not going to go into too much with that, but I just wanted to point that out. Here we go. So now the last thing I want to talk about is gas stations. To tie something together with all this electrostatic stuff, okay? The next time you're at a gas station, you need to be careful. The reason is this. Let's say your dad or mom gives you a gas can and says, hey, go to the gas station, fill this gas can up for my lawnmower. Okay, so you take the gas can, you throw it in the back of your car, maybe it's in the trunk or maybe it's in the back of a truck, and you drive to the gas station. Before you fill that gas can up, take the gas can out and put it on the ground. The reason is this. You could have a different charge on the gas can than you do or than the pump does. And if you actually go tap that gas can with the pump, if it's still in the car, it could actually cause an explosion. Okay? So be careful with that. So what you want to do the next time is take the gas can out, put it on the ground, and now the gas can is grounded, literally grounded, and it has the same charge as the pump handle. So when you go to fill that gas can up, it will have the same charge. Okay? Another thing is, let's say it's a really cold day and it's a dry day. So think about the scenario. It's a really cold day. You go to fill up your gas can or go to fill up the gas in your car. So you open up, you put in the pump, you start filling it up, and then you hop back in your car. Okay? You're waiting there, and then it fills up, you hop out. Before you grab that handle, you need to be careful because you could actually have a different charge than the pump. Okay? Now, a couple parts of why this could be the case. When it's cold, it's not so much if it's cold. And to be honest, I've noticed this even when it's a warmer day, but if it's dry. So if the air is dry, then that static charge holds a whole lot better than on a humid day, okay? But if it's cold, that's usually when you hop in your car, right? Well, if you hop in your car, think about what you're doing. Your butt is sliding against the seat going in, your butt's sliding against the seat going back out. You actually could have a different charge now than the pump handle. And when you reach for it, think about what's happening. The gas is filling in the tank, okay, but it's also, because it's shooting out fast, it's also mixing with the oxygen around that pump, okay? So if you go to grab it, you could create a spark between your hand and the pump. And if you got a bunch of gas mixed with oxygen, you could create an explosion. So the next time you do that, all you need to do is when you hop out of your car, before you go near the pump, just tap the top of your car. Okay, and you will ground yourself again, and you'll be the same charge as the car and the pump handle, the outside of the car and the pump handle at that time, and then you'll be safe. I'm like a doctor here. I'm saving lives. You're welcome, America. Okay, so that's it for electrostatics. The next lecture I give will be on electric current and Ohm's Law. All right, thank you.